Today's lesson is 11.5b. We're continuing with equations of circles. Just wanted to give you a quick review of where we've been so far in chapter 11. One of the first lessons was on congruent central angles, and if we have congruent central angles, then the chords that they make are the same and the arc measures are the same. A lot of times with these we would use the Pythagorean theorem to solve for the different lengths, so always be sure to draw in your radius to make a right triangle so that you can use the Pythagorean theorem. The next lesson was on inscribed angles. Inscribed angle is when the vertex is on the circle, and when we calculate those, the measure of the angle is half of the arc. Sometimes it gets confusing when they're kind of overlapping and stuff, so always remember to isolate the matching arc with the angle or vice versa so that you can figure out what it is. If we have angles whose vertex is somewhere on the inside of the circle, that means it's not on the edge and it's not at the center. The way we calculate those angles is we add up the arcs together and then take half of it. So it's kind of like taking the average of the two arcs. If the angle has its vertex outside the circle, then we take the two arcs and we subtract them and then take half. So it's very similar to when they're in the inside, it's just that we have to subtract them this time. The last thing that we can look at is actually look at the lengths of the chords. If the chords intersect inside the circle, I can take the two parts of one chord multiplied together, and that's going to equal the two other parts multiplied together. If the chords intersect the outside of the circle, it's actually the same thing, but you just have to always remember to start from a vertex, go to the edge of the circle, and then you have to go back to the vertex all the way to the other side of the circle. And so we have to make sure we include, that second time we have to include the whole length of that secant when we're including it. Here's some examples of his. This is an inscribed angle. If this arc measure here is 50, then the angle would be 25. Here we have an angle where the vertex is not on the center of the circle, it's not on the circle, and so it's right here on the inside of the circle somewhere. What we do is add up the two arcs, add up the 130, and then take half of them. So that would be an angle of 65 degrees. And if I look at it, that does look like it would be about a 65-degree angle. Here I have again an angle now whose vertex is on the outside of the circle. So instead of adding my two arcs together, I'm going to subtract them. So I would go 94 minus 20, which is 74, and then I would take half of that, so that would be 37 for that angle P. Here we're dealing with chord lengths. We can take the two parts of a chord, the X and the 10, multiply those together. It's going to be the exact same thing as 12 times 5. So 12 times 5 is 60, X times 10 is 10X, divide by 10, and I come up with 6 for this length. And that looks like that would also make sense. Make sure your answers always seem to be realistic to what the diagram is. The next one's talking about this chord length when the vertex is on the outside of the circle, and this one can look a little confusing, but you take the outside of the segment, then you take the whole secant, outside of the circle, the whole secant. So for this top secant, I did the outside, which is the 10, and then I did the whole thing, which is 10 plus 16. For the other secant, I did the outside, which is 12, and then the whole thing would be 12 plus y. Common mistake there would be say that that length is 12y, but it's not. We have to add it together. And whenever we have a number outside of a parentheses like this, we have to make sure that we do distributive property here. On this one, since we can add 10 and 16, we actually don't even have to do distributive property. We can just calculate it by multiplying. But I went through this process, did distributive property, and I came up with a length of 9.7 for the length from this edge to that edge on this circle. And the last thing that we've done in this chapter so far is the equations of circles. Equations of circles are always in this form: x minus the x term squared plus y minus the y term squared equals my radius squared. Center point goes in these two blanks. The length of the radius goes behind the equal sign. If your center point includes a negative term, then you can write it as x plus 7. That just make sure then you remember that that x plus 7 actually represents a negative 7 for your x term of your center point. So if I have this circle here, right now it has a radius of 3. I can see that because it's got the 3 squared, and my center point here would be -3 for my x term, positive 0.5 for my y term. And if I look at that picture, that does make sense. As I make this bigger, my center point stays the same and then inside that equation, and the only thing that's changing is my radius. If I move my center point to something else, now you can see that just this changed and my radius stayed the same. But again, make sure if this thing changes into a positive, that actually represents x minus a negative 2.5. They have to be a little bit careful with those plus and minus signs. So if I would give you this, if I wanted the equation of a circle with 1, -2 and a radius of 5, I can look back here just at these radiuses, and I can already see that I can knock out these middle two options because 5 is my radius, but I always have to do radius squared at the end. And so I know it's either the first one or the last one. When I look at my first term for x, it's 1, so I know in my first parentheses it should be x minus 1 squared, and then it should be y minus a -2 squared. So I know that this last one here would be the right answer for my equation of the circle. ACT does like this kind of question, so it's a really good idea to remember this format because they'll have those kind on the ACT. Next question now is, I want to know what's the center of this circle. Well, I can kind of just ignore this 36. All that tells me is the radius. I should know that this, if there's a 36 back here, then my radius actually is 6. But that's not what they're asking about. The only thing they're asking about is the center of the circle. And that's already in the right format with these minuses. So my x term must be just the 4, and my y term must be just the 5, which is answer C on this multiple choice. What's the radius of the circle with this same thing? Now we can see we can ignore this first part of the equation because that just gives me my center point back here. It's tempting to say that 36 is my radius, but we want to take the square root of that because we want to know r squared has to be 36, so I know that my radius here would be 6. On the next equations here we have some circles, and I would want to know what is the equation. If I was going to try to make this graph appear on my computer, what would I have to use to make this? Well, my equation, I'd have to have my x term of 2 and my y term of 3 for my center point. And if I look at my radius is 1. So if I look at the answer here, it would be x minus 2 squared plus y minus 3 squared equals 1 squared. Both of these have minuses in them like they're supposed to be, but the actual numbers are just the 2 and the 3. Now in this one, what do these circles all have in common? Do they have the same radius? Do they have the same centers? What kind of things could we say are the same about all these circles? Well, the first thing we can notice is that they have all this point in common. They all go through that exact same point. We would call that a point of tangency. So they all share that point of tangency of 0, 0. And they would all also have x minus 0 squared as the first part of their equation. Because if I look at all of these center points, they're all on the line of x equals 0. Their y terms would change because they're actually going up with the y terms. So they all share a point of tangency and their x value for their equation. On this one, if I wanted to make this appear onto my computer screen or onto my calculator, this is the equation that I'd be dealing with, because this top small circle here has a center point of 0, 7, and it has a radius of 1. That middle circle has a center point right here, which is the point 0, 3. So I did x minus 0 squared plus y minus 3 squared, and my radius this time is 3, so it's 3 squared. The bottom one down here now has a center point of 0, -5. And I could write this right here as y plus 5 if I wanted to. Just make sure you keep track that this is actually representing a -5 for your center point. And here my radius was 5. Here, all of these circles would share the same center point of 1, 2. So all of their equations would start with this. The second half of their equation would be changing because they all have different radiuses, but it's a concentric circles because they all share the same center. So this would be the same start for all of those equations. Here's your assignment. It's just going to kind of talk you through working more with equations of circles, and hopefully you're able to expand what you've done with that.